So, I'd like first to thank very much Astrid and Rinka for giving me the opportunity to present my work. When she proposed me this topic, I was first excited, but at the same time a bit worried because it's a challenging topic, and I know that there are eminent specialists in this room, so I hope we'll have nice discussions about this after my talk. And also maybe during my talk, I invite you to interrupt me if you need some more explanation during my talk. So, Armor layer physics. My talk comprises three parts. I will start with a kind of overview of the topic. Then I will go into the processes, and I will try to see what are the consequences in terms of morphodynamics. So, processes. Overview. Let's start with a short definition of armoring. So the armoring, the base armored when the base surface is coarser compared to the subsurface. I think that everybody agrees with kind of a definition. And we usually define armor ratio comparing the surface and subsurface median diameter. But we could go further in these definitions because we also have this debate between what is armor, what is pavement. I will not develop this today, but I can just recall that what is usually called armor is a mobile layer, the mobile layer, frequently removed and which could be seen in equilibrium reverse, whereas pavement is more usually associated with a static layer in a semi-permanent and degrading reverse. But I am conscious, I think that there is still debate on this between these two definitions. I'm not sure if it works, but okay. Sorry. So, and probably there is a link also between what we usually call pavement and armor. And I would like to add maybe in terms of processes, maybe there are a difference. Maybe we could have the armor could be more a result of the grain process, whereas the pavement could be a result of the hydraulic process. This is my personal point of view. Maybe we'll discuss that later with my presentation. Anyway, today's presentation concerns the armor in terms of mobile coarse layer, which is mobile and frequently removed. Okay, does not work very well. So the armor could be seen in any kind of reverse with rubber and cobalt materials, from step pools to large meandering reverse. And we can observe this kind of bed structuration at different scales. It could be partial or total, like for instance in these two rivers. Usually the armoring is associated with some kind of bed strengthening. Either locally, we define the clusters. For instance, this is the classification proposed by Enrique al. Which is an imbrication, a local imbrication of stones which strengthen the bed locally. But we usually also have transversal chain forces, like for instance in step pools, or with transverse strips in other rivers, which are actually cobalts and which are imbricated, and between them and also with the banks, which creates some kind of chain forces across the river. This is, I think, that what my church calls chain state, with these banks effects, which strengthen the structures by anchoring the chain forces. Tell me if my English is not perfect, because you can ask me a question on the detail. The armor is also strengthened by grain imbrication and, for instance, grain fining, clogging by fining, but I will pass quickly on this. What are the conditions of occurrence of the armoring? So usually we define this with a transport state, which is the ratio between the shear stress and critical shear stress. And according to my own experience, because we've done a lot of experience in the flume, we consider that the armoring is very optimum for a ratio between 0.8 and 1.3, but we could discuss this if people have other results on this aspects. When we use this kind of relation, it's one difficulty is to define the critical shear stress, of course, because it's easy to say it depends on the transport stage, but what is the critical shear stress to be used? So we see here some results from the literature, and we say that there are many definitions of the critical shear stress, depending if it was measured in the flume or in the field, and for which point size. So, I go fast. Some interesting results for D84 from two different studies, something which could be used in field application, because they were obtained with different data, but could give similar results. I go fast because it's not really the topic of my talk today. So, can we consider that armor is fully stable? If you consider that in the field you have this kind of shear stress distribution over the section, we don't have a homogeneous shear stress, but large variation and variability in the section. And if you consider also that, for instance, local high value shear stress can create local high transport stage because of non-linearity effects, we see, I recently did some kind of calculation by fitting a Euler function for the shear stress distribution, by backfitting the coefficient using measured payload transport. And when I use this model, I observe that finally, even for very low average shear stress ratio, we can have locally some values which are higher than the critical shear stress, meaning that because of the spatial variability in a given section, even for average shear stress which are very low, we can have locally some destabilization. We could have locally some destabilization of the armor. What does stop hammering? Actually, usually you consider that for transport stage higher than 2, the full mobility is observed. But some people think that it may be persistent during flooding. And also what we will see today is that maybe the armor can also be destroyed independently of the hydraulic as a purely granular process. To finish on this overview, to model, if we need to model the armoring, we need fractional equations. And we had a discussion yesterday on this with Rob Ferguson talk, and I invite you to look at this very good review from Gary Parker on the different tools that can be used for modeling armoring. So, I come to the main purpose of my talk. Ready? That worked very well. Okay, now what I'm concerned with today is what are the processes leading to the armoring construction. So Richard and Grifford identified 3 main reasons in the literature review. The first one is downstream and vertical wiring, which actually is an effect due to local disequilibrium between what is coming supplied by the stream and the transport capacity of the flow, leading to a transport of the material with a settling of the coarser ones at the threshold, at the shear stress which corresponds to the critical shear stress of this coarse material. The second aspect, second mechanism, is the equal mobility of all sides proposed by Parker and his colleagues, which means that the fine elements are protected by the coarse element when the bed is at rest, when the shear stress is below the critical shear stress of the coarse material. But as soon as this material is mobilized by the flow, we have some kind of regulation of the sediment supply to the flow, and we can, this mechanism could maintain a kind of equilibrium between what is transported in a given range. To finish, they identified a third mechanism, which is a traction probing, which actually I interpreted as a kind of clustering effect. In this effect, the coarse sediment cross over the fine sediments and settle when they encounter a fixed point and grow locally as a structure. So in these three mechanisms, two of them will be associated, one with a degrading local condition, the other one with a equilibrium. What I suggest that maybe there is place for gradation in this process. And also we try to see if finally all these different mechanisms participate to overall general equilibrium, dynamic equilibrium of the bed. So I come to the second part of my talk, which is constant processes. So I will try to discuss these aspects with some experimental results. So let's consider two situations for the transport of fine sediments. We have the first situation with what the coarse sediment is not mobile, and we can have a situation infiltration of fine sediments between the coarse one, as presented this morning. We can have the site-selective downstream wiring, and also some kind of hiding effect due to the protection of fine sediment by the coarser one. The second mechanism I would like to discuss today is the kinetic sorting. We had a lot of discussion also this morning about this. When the sediment, coarse sediment is mobile, it doesn't work very well. Okay. The sediment is mobile and we have very efficient transfer downstream of the fine particles. So these two, I can illustrate these two mechanisms with a simple, very simple and funny experiments without water. Here we use a mixture of sediments, and we apply first shear stress, local shear stress with air pulse, and secondly we apply a vibration with this structure, this mixture. So now for the videos we need to come here. Okay. So this is a little experiment, very simple, without water, just to see very well. So on the left you have the air pulse, and the right you have this vibration of the mixture, and you see the evolution of the sediment mixture in both situations. In both cases you have a coarsening of the surface, here with a transport of the finer sediments, and here with a migration of the finer ones. It's without water. It's just for, it's just to show the different mechanisms. Okay.
So earthquakes cause harm.
Yeah, sure. So.
Do you know the acceleration from the vibrations?
What do you mean, the intensity?
So the upward acceleration induced by
No, I don't have any measurement, just for visual consideration. It's not really an experiment actually, it's just a little funny video just to show the. Sorry. So usually we have both effects actually, because what we observe in the flow is a mobile coarse layer moving over a more static layer. And we can define two distances, one horizontal and one vertical, associated with the trapping of sediment. So we can see that on little movie. I have quite a few movies, so it's better for this time of the day. Here you have the transfer of sediment, a mixture of sediment in water this time, with, you can see if you look carefully, the fine sediment being captured by the coarser ones. They are transferred downstream, but the trapping is very efficient. You can see here, for instance, they disappear between the coarse mobile sediments. So here we have typically two distances, one horizontal distance of transfer of the fine sediment, and one vertical, which corresponds to the trapping inside the bed. So the vertical transfer is not very large. Usually it's no more than 1 diameter of course the coarser fraction. Because if you saw this photo, this is very famous. We saw it this morning. I was looking for the credit. I did not find it, but I think it's Johnson. I saw that this morning. No, this one. I did not put the credit, but.
How?
Okay. So we see this very clear distance of infiltration, and here in the flume we have exactly the same process, and in the field also it shows on measurement in the field. Concerning the horizontal distance of transfer of fine material in the flow, it's poorly documented. Actually, the trapping, we know that the trapping is very dependent on the ratio between the coarse and the fine sediment. We had a discussion of this yesterday and this morning. It's not the fine sediment is not necessarily sand. It's really this ratio which is important actually. The percentage of fine is important. I did not find any measurements showing what should be the optimum value of the percentage of fine sediment.
Could you make clear what LH exactly is? This one pop? What is LH in terms of distance?
Oh, sorry. Yeah, it's not appropriate here. What is called LS here is my LH in my previous graph.
What is LH?
So, if you put a mixture in a flow,
yes.
And you can, by sampling the bed, you see what is the extent of the infiltration of this fine sediment in the bed. The longitudinal extent of the infiltration in the bed of this fine sediment.
Okay, so that means that the fine particle enters the bed and it goes LH and then it's in the bed.
Yeah.
Okay.
This is there is really an optimum distance where you can measure this infiltration. We saw also this morning that depends density ratio. So in my experiment, I measured the distance. So this is what I explained just before by sampling the bed, and we can see that it also depends on the flow conditions. And actually, the higher the flow and the longer the disease distance. And if you consider a very high flow, what we observe actually is that its equal mobility, this length becomes very long. You don't have, you cannot measure a clear infiltration. It's you tend to obtain a very long length for the bed response to this kind of infiltration. So now we'd like to postulate discuss two postulates. The first postulate is that armoring initiates two antagonistic effects, and the second postulate is that it is a multi-scale phenomenon. So, what are these two antagonistic effects? We can imagine an bed, a self-made bed, by injecting sediment in a flow, and we can summarize by these two drawings. What we will be observed without armoring and with armoring. Actually, in both cases, we will have the same mixture of sediment, but a totally different exposure to the flow. And this exposure, this protection of the bed by the core structure would lead to a slope which is much steeper with an armor than without armor. So if you consider the same flow condition, but in one case the bed creates an armor, and in the other case you don't have any armor. So, but because of this very efficient trapping and the construction of the fine layer below the coarse layer, the armor is constructed actually over this fine sediment layer, and the final slope is steeper but unstable. This is the antagonistic effect. Actually, we create a bed which can be, in appearance, stronger and more stable, but actually this bed is fragile because below you have built this kind of fine sediment over which repose the coarse fraction. I will try to illustrate that